So, picture a conference room. Like specifically, picture conference room 7B at Google's Mountain View campus.
Right. Classic tech vibe.
Exactly. It's got that, classic vibe. Whiteboard, just completely covered in yesterday's tangled architecture diagrams that nobody bothered to erase. But the three engineers in this room, they're not even looking at the whiteboard.
No, they're looking at the screen.
Yeah. They're huddled around this single monitor in the corner, and they are watching something that basically upends decades of software development. They are watching code literally repair itself.
Which is, a scenario that fundamentally alters the physics of how we manage digital infrastructure today.
It really does. So welcome to the deep dive. And what we just described, it isn't some scene from a sci-fi script.
Right.
It's Google's CodeMender. And today, our mission is unpacking this really comprehensive, just fascinating piece from Aaron Rose in Tech Reader magazine.
It's a great article.
It really is. It charts how this AI agent graduated from like a quiet DeepMind research project all the way to a massive enterprise platform at Google I/O 2026.
And if you're wondering why this matters to you, the listener, it's because literally every piece of software you rely on has been trapped in this terrifying asymmetry for decades.
Oh, yeah. The gap between finding and fixing.
Exactly. Finding vulnerabilities is cheap, right? It's basically instantaneous now. But fixing them, that requires slow, incredibly expensive human labor.
Until now. Today, we are exploring how that gap is finally, closing.
Because to really grasp the magnitude of what CodeMender actually does, we have to look at the historical bottleneck here.
The pile of tickets.
Yes, the infamous pile of tickets. We've had automated discovery tools for years. Fuzzers, static analyzers, dynamic testing suites.
They're great at finding the cracks.
They are highly efficient at it. They can bombard a million-line code base and just light it up like a Christmas tree with potential flaws. So the failure point was never detection. The failure point was, like Aaron Rose calls it, the pile of tickets.
Right. So imagine it's the morning after this comprehensive vulnerability scan, right?
Mm-hmm.
An engineering team logs in, they pour their coffee, and they just find a literal mountain of critical alerts.
And every single one of those alerts represents a massive cognitive load for the team.
Because it's not just a quick typo fix.
No, not at all. An engineer has to open the file, reconstruct the entire mental model of how that specific module interacts with the broader architecture.
Which is huge.
Yeah. Then isolate the actual root cause, draft a patch, and then they have to run regression tests just to make sure their patch didn't introduce, a breaking change somewhere entirely different.
And in a code base with, 4.5 million lines, that single ticket can consume days.
Days where that vulnerability just remains live in production.
Exactly. The exposure window is entirely dictated by how fast a human can read. And this is where CodeMender, which runs on the Gemini DeepThink models, just completely changes the equation.
Because it's an autonomous remediation engine.
Right. It doesn't just surface a log file and say, hey, look here. It maps the logic, drafts the patch, and validates the fix. It's kind of like the difference between a really bad plumber.
Okay, I like this.
Who just, puts a bucket under a leaking ceiling, right?
Just catching the drips.
Right. Versus a master plumber who actually traces the pipes all the way behind the walls to fix the actual water pressure issue down in the basement.
That is a perfect analogy, actually, because the crucial distinction here is its approach to root cause analysis. Traditional tools, they just point to the presenting symptom.
The bucket,
where the program actually crashed. But CodeMender traverses the application's underlying logic. The article actually highlights this specific DeepMind test case involving a heap buffer overflow.
Oh, right, the XML one.
Yeah, so a standard static analyzer simply flagged the overflow event. But CodeMender mapped the entire data flow path backwards. It determined that the actual root cause was incorrect stack management of XML elements during parsing.
Wow.
And that was several layers deep in an entirely different module.
So it's literally like injecting a radioactive dye into a patient's bloodstream.
Exactly.
Like instead of just treating the localized swelling where the vessel burst, the AI watches the dye circulate through the whole dependency tree to find the microscopic clot that caused the pressure buildup in the first place.
And that mechanism, the way it does that, is powered by what DeepMind structured as a multi-agent validation loop.
Right, because it's not just one brain.
No, we aren't looking at a single monolithic language model just guessing at code. CodeMender splits the remediation process into 3 specialized adversarial agents.
Okay, walk us through how that handoff works. Because if the first agent is acting as the primary mechanic, tracing that data flow and drafting the initial patch,
Right.
how do we know it isn't just hallucinating a fix that breaks a completely unrelated feature?
Well, that is the exact problem the second agent is engineered to solve, the regression tester.
Okay, the tester.
So once the primary agent drafts a patch, it uses static analysis and SMT solvers, which is essentially translating the code's logic into mathematical constraints to actually prove its state.
Proving the math behind the code.
Yes. Then it hands the modified code to the regression agent. And this second agent isolates the modified module and just bombards it with the project's existing test suites,
Just trying to break it.
actively looking for downstream breakages.
So the first agent builds the engine part, and the second agent turns the key to see if the engine catches fire.
Basically, yes.
So what is the third agent doing?
The third agent acts as the judge. And this is an LLM specifically fine-tuned for code review and security auditing. It performs this strict line-by-line comparison between the original state and the patched state.
Like a senior engineer looking over your shoulder.
Exactly. It maps the abstract syntax trees of both versions to guarantee functional equivalence. It verifies that project-specific style conventions were maintained.
Oh, wow. Even the style guide.
Even the style guide. But most importantly, it analyzes the new logic to ensure the patch didn't inadvertently introduce a secondary vulnerability.
Like a race condition or something.
Or a privilege escalation vector, yeah.
Okay, but if the judge detects even a minor deviation or like a failed constraint, what's the protocol? Does it alert a human?
No, it immediately rejects the pull request and feeds the failure data back to the primary agent.
So it just tries again.
Yes. The system self-corrects and iterates in a closed background loop. A human engineer only sees the output when all three agents reach absolute consensus on a flawless patch.
That is wild, and that autonomous loop is impressive enough just for isolating a single bug.
Yeah.
But Aaron Rose's piece outlines a much broader application here.
It does.
CodeMender isn't just reacting to individual tickets. It is proactively eradicating entire classes of vulnerabilities.
Which represents this massive shift from tactical patching to strategic architectural hardening.
Proactive defense.
Right. And the most consequential feature highlighted in the text is CodeMender's ability to autonomously implement -f-bound safety annotations.
Wait, -f-bound safety. Let's break that down. By injecting those compiler annotations, CodeMender is fundamentally altering how the program handles memory allocation, right?
At a structural level, yes.
Right.
Because a buffer overflow occurs because C and C++ historically lack inherent spatial safety. They allow a program to just write data past the allocated memory boundary.
Which is how hackers get in.
Exactly. So instead of playing whack-a-mole with individual overflow alerts, CodeMender parses the code base and instructs the compiler to mandate runtime bounds checks for pointers within structs.
That's right, so it's applying a universal constraint. It's not patching a leak, it's permanently upgrading the pressure rating of every single pipe in the building.
And the retroactive application of this is where the scale just becomes staggering. The text references the libwep library vulnerability from 2023.
Oh, CVE 2023-4863.
That's the one.
That was huge.
It was a critical heap buffer overflow in image parsing that attackers weaponized into a zero-click exploit targeting iOS users.
Zero click, meaning a threat so severe the user didn't even need to interact with a malicious payload to be compromised.
You didn't even have to click a link.
Terrifying. So how does CodeMender change that?
Well, DeepMind researchers ran a historical simulation. They pointed CodeMender at the pre-2023 iteration of that library. And CodeMender autonomously applied bound safety annotations across the library's entire architecture.
It's on its own.
On its own. And had those compiler-level constraints been in place back then, that specific 2023 zero-click exploit
Wouldn't have worked.
along with almost every other memory corruption flaw native to that module, would have been mathematically impossible to execute.
Wow.
The entire threat class simply ceases to exist.
And Google is already deploying this at scale, right?
Yeah.
Like the article mentions, in its first 6 months alone, CodeMender upstreamed 72 validated security fixes directly to major open source projects.
72.
And they were navigating code bases containing upwards of 4.5 million lines of code.
Which forces us to really look at the timeline here. DeepMind published their quiet initial research paper on this system in October 2025.
Okay, October 2025.
Just 8 months later, in June 2026, Google unveiled CodeMender at I/O as a fully integrated multi-billion-dollar enterprise platform.
Which is insane. In the context of enterprise infrastructure development, an 8-month pipeline from a research white paper to a flagship commercial deployment. That is practically instantaneous.
It's unheard of.
But the text makes it clear that Google didn't accelerate this launch in a vacuum, did they?
Yeah.
The urgency was a direct response to a massive shift in the threat landscape.
Triggered by Anthropic.
The Anthropic catalyst.
Right. In the spring of 2026, Anthropic released their Mythos model. Now, the security community had long theorized about autonomous offensive AI.
Sure, AI that attacks.
Right, but Mythos provided the empirical proof. Anthropic actually demonstrated that a frontier AI could autonomously traverse complex operating systems, web browsers, hunting for zero-day vulnerabilities at pure machine speed.
And Mythos wasn't just finding known bugs, right? It was discovering novel, undocumented flaws.
Yes.
And chaining them together into viable exploits without any human intervention.
It fundamentally broke the structural math of cybersecurity.
Because humans are too slow.
Exactly. A human defense model relies on asynchronous patching. An engineer triages a report, they write a fix, they push an update. But if an offensive AI like Mythos can map a system, find a logical flaw, and execute a zero-day exploit in literally milliseconds,
then the human defense cycle is structurally obsolete.
the backlog crushes the security team instantly.
Wow. Defense literally has no choice but to operate at AI speed.
None. CodeMender is Google's required countermeasure to a world where Mythos exists.
Which makes so much sense.
Yeah.
And the acknowledgement of that reality led to one of the most remarkable moments at Google I/O 2026.
Oh, Sundar Pichai's keynote.
Yes. Sundar Pichai stood on stage and explicitly credited Anthropic.
Which you never see.
Never. He stated that Mythos proved the necessity of massive-scale models for real-time security use cases, right before asserting Google's capacity to, meet that challenge.
Yeah, for a chief executive to offer unprompted, on-the-record validation to a primary competitor's model,
It's unheard of.
it highlights the severity of the paradigm shift. The physics of the industry changed. Corporate posturing just had to take a backseat to actual survival.
So that realization brings us to the actual logistics of enterprise deployment. Because an autonomous remediation engine is a brilliant piece of computer science, obviously. But integrating it into the operational backbone of global corporations, that requires an entirely different architecture.
Oh, completely, which explains Google's $32 billion acquisition of the cloud security platform Wiz in March 2026.
$32 billion. So how does Wiz fit into this?
Wiz provides the sensory network. It continuously maps live cloud environments, building these highly complex graph databases of a company's architecture. So it identifies attack paths and prioritizes them based on business impact. It's not just flagging a vulnerability because it exists. It's flagging it because it provides a direct, highly reachable path to, say, a core customer database.
Oh, I see. So Wiz acts as the autonomous scout, prioritizing the targets. And CodeMender serves as the autonomous mechanic, actually generating the patches.
Exactly. The integration creates a closed, continuous loop. Wiz surfaces the critical exposure in real time, and CodeMender instantly initiates the multi-agent remediation cycle to neutralize it.
But I have to challenge the reality of that deployment, though.
Go for it.
Because Aaron Rose quotes Chris Steffen, the VP of Research at Enterprise Management Associates, and he points out a massive hurdle here. If I am the chief security officer of a Fortune 500 financial institution,
Right.
I am absolutely not allowing a standalone autonomous AI to push untested code directly into my live production environment,
No way.
regardless of how good the LLM judge claims to be.
And Steffen is entirely correct. A rogue autonomous agent modifying core infrastructure is an absolute non-starter for enterprise risk management.
So how do they get around that?
That is exactly why Google integrated CodeMender directly into their agent platform. It does not operate freely. It sits behind strict API gateways governed by robust identity management and comprehensive observability protocols.
Okay, so it isn't just an independent contractor wandering the building with a wrench.
No.
It's an employee operating within a highly supervised corporate pipeline with rigid access controls.
Precisely. Every action leaves an immutable audit trail. CodeMender precomputes the patch, runs the regression suites, isolates the blast radius, and presents a high-confidence, fully validated artifact.
But it can't deploy it.
Exactly, it cannot deploy it. The architecture mandates a human approval workflow as the final gate.
Okay, but doesn't that just reintroduce the exact human bottleneck we are trying to eliminate?
Yep.
I mean, if CodeMender is neutralizing threats at machine speed and submitting 1,000 patches a day, a human engineer clicking approve isn't actually reviewing the code. It just devolves into alert fatigue, right?
Hmm.
The human becomes a rubber stamp.
You've hit on the core friction point of human AI teaming and security, but Google attempts to mitigate that alert fatigue through the Wiz integration.
How so?
Because Wiz prioritizes the alerts based on actual exploitability and real business risk, the human security team isn't bombarded with 1,000 minor syntax tweaks.
Oh, so they only see the big stuff.
Right. They are only reviewing highly critical, complex architectural patches. The noise is filtered out.
Which leads directly into the broader conversation about guardrails and weaponization.
Hmm?
Because an AI that understands code-based logic intimately enough to patch it.
Also understands how to silently break it.
Exactly.
And the dual-use nature of agentic systems is a primary focus of Google's policy framework, beyond the multi-agent consensus loop we discussed,
The three agents.
which is engineered to catch functional deviations before they reach the approval stage. Google also launched SAIF 2.0.
The secure AI framework.
Yes.
They also initiated a dedicated AI vulnerability reward program, didn't they?
They did. They established a continuous bug bounty, paying external security researchers to actively probe CodeMender's internal logic constraints.
Basically paying hackers to hack the AI.
Exactly. They are crowdsourcing the stress testing of the AI's alignment to ensure it cannot be socially engineered into introducing a backdoor or bypassing the LLM judge's security parameters.
Right, but even with those external audits and, internal API gateways, Aaron Rose's piece returns to a deeply human question.
The human element.
Yeah. If this system successfully absorbs the massive backlog of vulnerability management, what actually happens to the human engineers who currently do that work? Are they out of a job?
Well, the article frames the answer by taking us back to that initial scene in conference room 7B.
Right, with the three engineers.
Right. After CodeMender successfully deployed that 30-second patch for the heap buffer overflow, one of the engineers pulled up the system's internal reasoning trace.
The log of how it thought.
The log of how the primary agent evaluated the constraints and mapped the abstract syntax tree. And the engineer noted that reading the trace didn't feel like parsing robotic output.
What did it feel like?
It read like a highly technical peer debugging session.
Oh, wow.
The engineer's conclusion was that CodeMender isn't replacing the development team, it's absorbing the systemic grind.
The grunt work.
Right. It takes over the tedious root cause archaeology and the exhaustive regression testing that historically just burns out security teams.
So it acts as a force multiplier.
Mm-hmm.
By automating the defense against machine speed attacks, it frees up human engineers to focus on complex, forward-looking architectural design that requires actual human judgment and creativity.
Exactly. We have spent decades accepting a reality where finding a critical flaw takes milliseconds, but neutralizing it takes weeks of manual labor.
The asymmetry.
Yes. And by integrating massive LLMs with multi-agent validation loops, CodeMender finally balances the scales. Defensive remediation can finally operate at the speed of offensive discovery.
And, while the massive enterprise cloud deployments obviously dominate the headlines, this autonomous architecture is already active in the wild today. CodeMender is currently auditing and securing the foundational open source libraries that billions of people,
including you listening,
including you, interact with every single day. The digital infrastructure running your life is actively being repaired right now by invisible agents.
It's essentially a silent, autonomous maintenance grid operating beneath the surface of the internet.
It really is. And it fundamentally reshapes how we think about software reliability. But it leaves us with a highly provocative scenario to consider as we wrap up.
What's that?
If defensive AI agents like CodeMender and offensive AI agents like Anthropic's Mythos are now both operating at pure machine speed, what happens when they inevitably collide?
That is the million-dollar question.
Right. Imagine a malicious AI and a defensive AI locked in a real-time, millisecond-by-millisecond battle over a system's core logic. As these agents continuously map, exploit, and literally rewrite the codebase on the fly to outmaneuver each other, will the final, ultra-secure software they leave behind even be readable by the human engineers who originally built it?
It's an incredible thought.
Something to chew on.
Keep questioning the invisible code running your world. We'll catch you on the next deep dive.